greet you all here for this Harold N. Shapiro. As you'll be hearing, N stood for noisy Shapiro. There was also a silent Harold Silent Shapiro here at Courant. And this will be a lecture now, given by our distinguished visitor and twice a former colleague here at Courant, once together with Harold Shapiro, Peter Sarnak of Princeton University and the Institute for Advanced Study. I'm very grateful for him accepting our invitation to take this opportunity to honor Harold and the wonderful memories we have of him. Just to tell you a little bit about the schedule, we're going to have the talk here, and then later there'll be a reception around 7 or so back at Courant Institute on the 13th floor lounge. There'll be food and drink, and there will be some recollections of Harold by some colleagues and friends and so on, and a representative of the family. And we look forward to having you join us for all of those, this evening. So I think that Peter Sarnak needs no introduction in many senses. So he's going to be talking to us about Markov triples and graphs and strong approximation. And we look forward greatly to hearing this. So thank you.
That's a great pleasure to be back here to honor Harold Shapiro, who I will make some comments about later in terms of his personality and his impact on me. Also, it's great to be back at this seminar, which Dorian and I, and maybe Spiro and Kollybagen introduced many years ago. At the time, it was a new seminar, and today it's considered one of the great seminars, number theory seminars around. So it's a great pleasure to lecture in the seminar as well. So my plan will be to spend some 15 minutes on a particular problem that Harold Shapiro was very interested in, and that will lead naturally into the problem that I'll discuss, which is something I think he would have enjoyed. So his style was very different to many mathematicians. Well, let me tell one story quickly. When I first came here, he told me that Tate, and this is true, there was a woman by the name of Matchett, Margaret Matchett, who was a student of Tate, of Emil Artin in Indiana, when he was still in Indiana, before he came to Princeton. And Tate had this idea of a thesis about ideals, ideals, and proving Hecker's work in this very conceptual and beautiful way. And this lady, I think her name is Margaret Matchett, did in fact write a paper on ideals in Indiana. And then apparently when he came to Princeton, he had many great students, of which one was Harold, another one was John Tate. And he was offering this as a thesis project, and Harold Shapiro thought, well, no, he's thought about it already. I want to do something that's completely my own. And he turned it down. This became Tate's thesis, and it's one of the greatest theses ever written. It might be called Harold Shapiro's missed opportunity. But the first thing he said to me, do you know that I was offered Tate's thesis? There are very few theses that just go by the name Tate's thesis. I don't even know another theorem that's so-and-so's thesis. Anyway, apparently Harold had his own ideas. He was a student of Emil Artin, and he clearly liked the elementary side, the difficult problems, and ones where he could invent his own ideas on a problem. And that's what I'll discuss here a bit, and it's about primes in very sparse sequences. Very sparse. Well, we'll start with sparse and sparse. Something that's fascinated many people for many years, but sometimes a problem is so hard that nobody even tries to do anything on it. But not Harold. He wanted to say something non-trivial on a very difficult problem. So suppose I take f a polynomial, integral polynomial, of degree greater equal to 2 to make it interesting. This is degree 1. It's a famous theorem of Recurrence.
One variable?
Right now it's one variable. All right, f of n. So I want f of n is f of n prime infinitely many. Well, if you take something like n squared, you can probably answer it. So, so for example, n squared plus 1. Mankind doesn't know. We know in here solving this. We are certain that there are infinitely many primes of the form n squared plus 1. So there's no serious quadratic polynomial for which the answer is known. So that's not very sparse, it's just a little bit sparse, and already we're stuck. What you can do is a very famous work of Brun, which is still the best on this kind of problem, any polynomial. Vigo Brun invented something called the sieve. All started with him, modern sieve, combinatorial sieve. And while it doesn't produce primes here, it limits the number of primes. It gives an upper bound for the number of primes. So it gives the right order of magnitude, correct? It's a highly non-trivial thing. It's elementary, but as Harold Shapiro, I think, would have appreciated, and I think very much his style, elementary does not mean easy. It means it's much harder, by the way. It's very easy to work big machines without knowing what you're doing. If you come with a bulldozer, things look quite easy. But if you just have a chisel, it's kind of tough. And the whole point here is that as soon as I change this problem, we have no tools whatsoever. And that's what appealed to him, apparently. So it gives this Brun sieve gives the correct order of magnitude for the number of primes less than or equal to x of the form f of n. So the number of m less than or equal to x, say, such that f of n is a prime. It's an upper bound which is just off by the constant. Correct order of magnitude only off by a constant, by the constant factor, by a constant. So. And in this Brun sieve, what you certainly have to do first, if you ever want to understand, it's a sieve that goes back to Aristophanes, is you look at the numbers, you look at all the numbers which are divisible by 2, you remove them. You look at all the numbers divisible by 3, you remove them. Then you add back the numbers that are divisible by 6 because you remove them twice. So you do this inclusion, exclusion. So you need to know one thing, if you're ever going to execute any kind of sieve, is what about the what's the behavior of f of n mod p, or mod q? So if I reduce f of n, as I go of the sequence n up to x, what is happening to these numbers in the residue classes modulo q? That's not difficult. I assume this was an integral polynomial, because the reduction of f of n modulo q only depends on what n is modulo q. So that's periodic. And so the number of solutions will then reduce to counting things in a periodic set. And then if x is very large, the number of integers which are in a progression is roughly the x divided by the length of the progression times the number over a progression. The number of a progression will quickly become interesting. It'll be that's highly non-trivial, but that's algebraic number theory. And if we have several variables, later we will, then that will be counting the solutions modulo p. That's arithmetic. That's of a finite field. That's where algebraic geometry comes to be very powerful. So the Brun sieve, the ingenuity of Brun sieve is that he was able to understand this inclusion, exclusion, and cut it off combinatorially and still get an upper bound inequality by not going too far. If you have to go inclusion, exclusion all the way up to the size of the number, then the statement that the number of integers congruent to the given number modulo q but less than x, if x is less than q, then it influences nothing anymore. Okay, so that is the kind of thing that exists. This is a powerful tool, and it's just hopeless already to our present understanding to produce primes yet. One can produce almost primes, but that's not the direction that I want to go, or the direction that Harold Shapiro is taking. So let's get much more ambitious. Let's look at a more Lachenry sequence. Let's look at 2 to the n plus 5. Is that prime infinity? Okay, this is just obvious. We believe it is. We don't believe there's any conspiracy unless there's some obvious divisibility, which I might have overlooked, but unless there's some obvious reason. But can we at least study that modulo p. Can we see what happens when I reduce this sequence modulo p? So firstly, is this prime infinitely often? The answer is we don't know. Is this composite infinitely often? Well, that's easy to answer. Because if I reduce modulo p, it will be asking, so if I look mod p, and then I'm asking, is 2 to the n plus 5 maybe congruent to 0 mod p? Is that divisible by p? So is 5 in, so 2 is an element in the multiplicative group, p is a prime in fp star, and I'm asking, do I hit 5? Do the powers of 2 hit 5? So now we're getting actually, probably, I'd imagine that with Harold Shapiro, there's something called Artin has a big conjecture and a small conjecture and many other things, but the small conjecture is the primitive root conjecture, which is still unsolved. The big conjecture is Artin representation, Gower representations, also unsolved. But there's progress on both. For example, Hooley was able to understand whether 2 is a primitive root modulo infinitely many primes if you assume the generalized Riemann hypothesis. So these questions of just what's happening modulo p are really extremely difficult on a Lachenry sequence like this, unlike this where it was kind of straightforward. So much so that Hooley, who wanted to execute a sieve on a thin sequence like this, even after inputting the Riemann hypothesis at the end of his book, his dream problem, at least at the end of the book, is to show that this is composite. It's clearly composite for infinitely many n's, but he wants to prove that for almost all n, so if you look at the number of n's up to x, for how many n's up to x is 2 to the n plus 5 prime, you should expect that to be little o of x. Most numbers are not prime. You should always expect that's density 1 over log. And that's what he wants to prove, and he's willing to assume the Riemann hypothesis for abelian L functions to get the Artin conjecture, and then he's even willing to assume some, and then he has to assume some other things, and eventually under various assumptions he proves his statement. But this is an illustration of how difficult it is to say anything over a sequence like this. Okay, well Harold Shapiro is not satisfied with that yet. Let's take 2 to the 2 to the n. Okay, I'm not an expert on this. This is, I think Fermat, I believe these were primes. And I don't know if this is a true story, but I understand the shortest talk at the International Congress of Mathematicians, maybe this is somebody made it up to me, but it's such a good story, I have to tell you. The shortest talk in the history of the International Congress is, so I think Euler showed that one of these are called Fn, one of these Fs, he factored it for mine and said, okay, you're wrong, they're not all prime. This one's not prime. Today on a computer you can do this, but not for n very large, because it gets very big. N doesn't have to be big before that's out of the range of any factoring algorithm. But apparently, maybe it was F7 or something that wasn't known in the 30s. Right? Is that correct? Is it a true story? The guy came in and his lecture was F7 is not prime, and all he did was he wrote F7 down, and then he wrote 2 numbers and he multiplied them longhand for 20 minutes, and then he got that side and he left. The proof by demonstration. I factored it for you. But today, I think there are computers trying to understand these questions in terms of increasing n. But Fermat believed they were all prime. He's wrong. It could be that all of them for n bigger than 20 are prime. You could say all of them are composite for n bigger than 20. You can say what you like. I can't disprove nobody. We don't know. In Hardy and Wright's book, very early on they discuss this question. They talk about primes. Is that number prime for infinitely many n? And they give a probabilistic argument based on the fact that the number of density of primes near a number is 1 over log of that number. And then you can assume that the primes are just randomly coming down like this. This is very close to the ranks. And run a Borel-Cantelli argument. And if you assume these things are independent, you will probably convince yourself if somebody put a gun to your head and said, if you get it wrong, I'll shoot you, then you'll probably believe this argument that there are finitely many Fermat primes. That's probably the truth. I mean, if you want, but you can say what you like. Okay, so these are just, it's like pi. Pi is supposed to be a normal number. Nobody normal tries to prove that because it's just too hard. There are problems that we don't have tools. We don't start. You don't know where to start. Okay, so Harold Shapiro decided he wants to do this problem. But you have to change a little bit. And so I'm going to talk about two papers of his. The first, and both are quite ingenious. They both appear in the Communications of Pure and Applied Math. The one is with Gerson Spera. Anybody know who this person is?
Spera.
No.
Okay. Was he a student of his?
Yes, and
Yes,
Harold,
yes.
Harold was very proud of him as a student.
It's a 1972 paper in which they are studying this.
It's who is there? Oh, Gerson
Harold Shapiro. It's a joint paper.
Oh, with Shapiro.
Yeah. And so they change the problem a little bit. So basically, they discuss many problems and they take a very modest attitude. They want to show the infinitely many integers in the sequence which are composite. That's all. Okay, so you saw that with n squared, or this composite is very easy because I could take modulo some 7 or some number where I hit it and then I'll hit it because things are periodic, but things are no longer periodic in this picture. And so nothing is obvious, and that's why we don't know whether this is composite from some point on or whatever, we just don't know. And I don't believe much more is known besides what they proved there, at least from what I could see from more recent things, there wasn't anything particularly interesting. So they look at this kind of sequence and other sequences. This is double exponential, single exponential, and they prove a theorem. So let me just give you the type of the theorem and then an example, which says that if you take 2 to the 2 to the n plus r of n plus 1, where r of n can't be identically 0, otherwise you would get Fermat's sequence. So r of n is exponential. So this is doubly exponential, so it's only exponential. So you can imagine what that means. So it's polynomials times exponentials. Exponential with some mild sum, some hypotheses connected with heights. I don't want to go into the proof of this. I'm going to explain the proof of another thing. Connected with heights of some points, but it's something that you can verify in many, many examples. So it's verified, this condition on R of n. And R of n, it's a non-degeneracy condition, so R equals 0 is no good. But the theorem is if these are satisfied, so if you perturb Fermat's sequence, if these are satisfied, then the sequence 2 to the n, 2 to the 2 to the n, plus R of n, plus 1, is composite for infinitely many. Producing primes even on n squared plus 1 is hopeless, so you're not going to be producing it.
I'm sorry, I don't familiar with the hypothesis.
I didn't say what they are. I'm going to give you an example. I'm just saying some generic hypotheses which are very complicated, but given an R of n, you can try check it. And for example, the following works: 2 to the 2 to the n plus 2 to the n plus 1. And it's not chosen so that it's just factors in the trivial way, otherwise you wouldn't know. It's highly non-trivial. And they have many other examples. So the paper is concerned with a very superlacunary things like this, where they have degrees of multiple exponentials under which they can prove something highly non-trivial by completely ad hoc elementary methods and algebraic methods. I want to rather describe a theorem which is a little closer to what I'll be talking about, because it's got a dynamical point of view and it's got some very interesting arithmetic modulo p, which is completely non-standard. It's exactly the style of what he liked. And that's a paper, and this I will explain a little bit the proof of and the exact statement, because this theorem sort of stands to me quite remarkably as a singular theorem. This with another, I assume, student of his, Foreman. Anybody know that name? Another student of his?
Yes.
So this was in the Communication Pure Applied Math. Seems like he had a monopoly in the Courant journal. You just go to Natasha Brunswick, say, here's my paper, please find a referee who's friendly. Both are great papers. This one I like very much. I'm going to tell you something very concrete And it's unique. It's a bit like Apéri's theorem. It works for this and then fails for everything else. So they're going to try prove this kind of composite statement for a Lackenry type sequence, which is exponential. And the thing they were interested in is the following, but it's not one where you can see any periodicity easily. So you take a real number bigger than 1, and you take the integer, you take it to a power n, and you take the integer part. This means the integer part. Theta is a real number bigger than 1. Okay? These are quite tricky. Of course, if theta is an integer, it's not. If theta is a Pizarro number, it's easy too. That they eliminate instantly. This is most interesting if theta is a rational number, like 3/2. I'm going to return to this. It's 3/2 and 4/3. These are the only numbers for which something is being proved. Now the expectation here is for any real number bigger than 1. This is composite for infinitely many n. There's no reason that it should be. Okay, you know, there are many crackpots who are going to give you a formula for primes. And there are even crackpots. There's this amazing, the set of primes is Diophantine, proved by Martin Davis, Matusevich, Julia Robinson.
What's his name?
Somebody else, yeah. there were 3 of them in Matusevich.
Putnam. Hillary Putnam.
Yeah. Anyway, so you can make a polynomial in 26 variables. I've even seen it written down. Because 26 is convenient with a number of. In its positive values. This is absolutely critical. Yeah, in New York City. By the way, the very first time I ever lectured in New York City, they said ignore anybody who's like coming and threatening you with doing something unusual because it's best to keep away. All right, so so the issue here is we're not going to ask if this is prime, it's too difficult, but we're going to ask if it's prime infinitely often, is it composite infinitely often? Exactly that question. Both first papers. And not positive density, just composite infinitely often. Okay, the first remark there, which is a very beautiful remark. Number 3/2 to the n, by the way. If you take 3/2, more generally, if you take theta to the n, and you take the fractional part, this is the fractional part, so you write theta to the n as the integer part plus the fractional part. Fractional part is a number between 0 and 1. You can ask how that's distributed between 0 and 1. And it's a simple measure theoretic theorem that for almost all theta bigger than 1, this is just due to Borel, I think. No, measure theory Borel. Anyway, it's just a simple argument, probabilistic argument, that for almost all theta, this is equidistributed in 0, 1. But you find me a theta for which it's true. That's extremely difficult. we can't find things like that. And in the case of 3/2, it's got quite a history because it's connected with the Waring problem in a kind of silly way. But it became popular especially because Mahler started writing a lot of papers about 3/2 to the n modulo 1. If you do a numerical experiment, you'll see it's perfectly equidistributed modulo 1, but there's no tools to tackle anything like this. Okay. If you take theta for which this, so say theta to the n, 1/n, they make a nice remark because this is going to be the philosophy that we're going to apply with theta's 3/2. Suppose theta to the n times 1/n is equidistributed. See, the problem is we don't know how to reduce modulo p in this integer part and then say, it's running between these residue classes, it's going to hit 0 infinitely often. Because it's the integer part. This is a hard thing to deal with. But suppose this is equidistributed mod 1. Well, that would mean that 1/m theta to the n is the integer part of theta to the n over m. I'm fixing m fixed. An integer, m greater than or equal to 2. Plus some error, which is between 0 and 1, and epsilon n, it's equidistributed. Epsilon n will be less than 1/m, bigger than or equal to 0, for a positive proportion of n. That's what equidistributed means. The proportion being just the length of the interval. n's. Well, if that's true, then clearly the integer part, if I multiply here, I'll get the integer part of theta to the n, is m times this integer, theta to the n over m, whatever it is, this integer, plus something which is less than 1. That's why I chose this number to be less than 1 over m, plus something which is eta n between 0 and 1. And hence the integer part of this is divisible by m, positive for an positive proportion. So for almost all theta, it's clear that these are going to be composite and provably composite. But as I said, put theta equal to 3 halves, which I'm interested in, or 4/3, or any integer, any rational number, a over b, bigger than 1. There's absolutely no doubt in anybody's mind that that's composite for infinitely many n. And the only cases we know are these two amazing theorems of Foreman and Shapiro, and it's true for 3/2 and 4/3. And the proof breaks down once the number gets bigger. The strategy is clearly the same. And I said it reminds me very much of Apari's proof of zeta of 3 is irrational. It works for zeta of 3, but it just doesn't work for zeta of 5. All bets are off, and zeta of 7. So somehow, and there are theorems. So there was one progress since this that I could find, since this remarkable theorem, where somebody had proved, well, of a list of numbers, there's at least another number for which the statement's true besides the two of theirs. And that's also been proved for zeta of 3, zeta of 5, up to zeta of, I don't know, odd numbers, zeta 11. So zeta of 3 is irrational. That's Apari, and we know that at least one of these other 7 numbers is also irrational. A theorem of Rivuel and Ball. Quite a remarkable thing. Yeah?
Can you get any clue how that seems a very strange theorem? How could that get proved?
It's because you write down linear form, instead of just, so, okay, now that would take me too far afield to prove irrationality of zeta 3. I'm just saying,
No.
that's what I'm going to explain. No, Shapiro will explain to you just the basics of that. Now, this I do want to explain. So how are we going to do, so let's take 4/3. Okay. So here's the idea. This is Shapiro's idea. Form. So the idea is, clearly I want to understand something like a over b to the n, the integer part. So it's 3/2, say. I would like to take a prime p. These are integers, and look at them, what residue classes they hit mod p, and I would like to force to hit the residue class 0. If I can force I hit 0 infinitely often, then that's my certificate for I'm composite. I'm divisible by that prime. All right, so you get a certain recurrence relation if you work it out for easily. So if you write a over b to the n as un plus theta n, and then take n plus 1 and do some little algebra, which I won't do, you get the following relation. Clearly the number a over b.
UN is meant to be an integer?
Un is an integer. Un will be an integer. Now I'm going to do, you multiply by a over b, and you multiply, cross multiply by b, you get the following relation. B times un plus 1 equals a times un plus en, this is all for n greater than 1. And of course a and b were relatively prime. And en is between minus b and a, and un, the whole sequence, and en, all integers. Okay, this is elementary. Now what you're trying to show is, of course, un is the integer part of what you want. You want to show that un is divisible by some prime p, by some number. So you want to study this recurrence relation, which is, if en were given to you, if en were a deterministic sequence, like 1, 1, 1, 1, 1, then you can solve that easily, and you can easily see what's going on, because it's just a first order recurrence. But the whole point here is that en is jumping around. You don't know what it's doing. It's just jumping around here to make that an integer. So they have to handle, no matter what en's doing, they have to handle it. That's the philosophy they're going to do with some pigeonhole argument. to handle no matter what En is in a way I'll explain right now. Anyway, so you want to show that Un is divisible by some P, and the P you're going to choose. So the P that's going to work for 4 over 3 turns out to be 5, and the P that works for 3 over 2 is 7. And then it hasn't worked on any other example, and I challenge you all to give it one new case. It really is something quite remarkable. In terms of 3 halves to the n, it's really the most interesting theorem now. Okay, so what you do is you're going to study this, and you really don't know what En is, but they have a few. Let me just start with a couple of lemmas, all of which are elementary, and you'll see how they fit together to give some information. But the idea here is that you're doing some kind of iterative dynamics, mod P of the field of Fp, but the dynamics is not something anybody's familiar with. In other words, you've got a driving force here. Think of this as a driving sequence, which you don't know. It's jumping around in order to make that an integer. Now, it's clear that the most important thing here is a number b over a. So if I work mod P, then let's let lambda equal a over b over a, b over a mod P. So firstly, I'm going to assume that P doesn't divide A or B, so it's relatively fine to both. And now I'm working all the time in FP, Z mod P. Then you can work out that the following numbers are very important. So let Sn be the reduction of the following sequence in Z mod PZ. I'm trying to show that Un will be divisible by P. And Sn is the following, the numbers of this form. So imagine lambda I equals 0 to k, lambda is this number in the finite field, b over a inverse, which makes sense minus P. Lambda I, E, N, no, plus I. This is for k equals 0, 1, 2, and so on. So these are numbers in this finite set of P elements. And I want to make sure that Un is divisible by P, and clearly this sequence here is what you get by iteratively solving this recurrence with the e's. So they let Un be the cardinality. This is the cardinality of Sn. And it's clearly somewhere between 0 and P, and they're very interested in when this is less than P. And now they've got some elementary lemmas which come from the recurrence. And then I'll just get to the key combinatorial point. And it's as follows.
What is Sn?
Sn is the set of numbers, the distinct residue classes, mod P, that you get by running through this infinite, by just reducing these guys, mod P, with different e's here. But the lambda is the important thing, because the lambda is the thing that was driving the recurrence at the multiplicative level, the e's at the additive level. All right, so they have some simple lemmas like if. So now, from now on, I can assume that Un is not 0 mod P for n bigger than n. Because if Un is 0 mod P, we're done. So either there are infinitely many primes that are divisible by infinitely many of the sequence are divisible by P, in which case this is proof by contradiction. Assume this is not true. Then from this, they're going to conclude many things about the set. This implies that nu of Sn, this is just simple algebra, is less than P. You miss one, these reduced things miss at least one class. And 0 is in Sn. We'll see that in a minute. So these are all consequences of this proof by contradiction. Also, if you take Sn, and you take En plus lambda Sn plus 1, this is a set, and you multiply that set by lambda, you get a new set, add En. This is true for n greater than or equal to n. This comes from this assumption. So Sn might be just one element less than the whole set. But this is already, you don't know what En is, but this is you know what lambda is, that was A over B. But you don't know what En is, and you have to face that. So anyway, this and 0 is in Sn. So these are all consequences of this. And then the next thing they observe is if En itself is periodic, well, that we can all do. If I have a difference equation in which the coefficients are periodic, it's like a flow K multiplier. You can write down a solution and study it completely in terms of explicit answer. So they now are in a position where they're looking at all this, and they have En, by the way, remember En was between minus A, minus B and A. So it's like it's 4/3, it's squeezed. There's not many choices for En. Can't be periodic because you get a contradiction. And this over here, you put some other constraints just by looking at the various configurations. So for example, for 4/3, which is much easier than the case of 3/2, they quickly reduce to the case where they can take P, as I said, equal to 5. That's the key marital number for which all the combinatorics works. So they take P equals 5, and they show that the ENs are the only possible way that they're not immediately getting a contradiction is EN plus and minus 1. And of course, it's not periodic, so they have to switch infinitely often themselves. So they quickly, by taking P equal to 5, are left with En equals plus minus 1 only. And then there are 7 cases they have to analyze by looking at the configurations of En plus 1, and En plus 2, all of which would lead to a contradiction. So it's something extremely special because the ENs are in very few sets, and combinatorially the ENs can't arrange themselves so that they're not going to be divisible by 5, as 5 in this case. So they actually tell you which prime is going to divide this infinitely on. You make A over B any other number and the proof fails. So it's very similar to a priori. It's like a priori is an approximation of zeta of 3 by a rational number, a very good approximation coming from a hypergeometric function. That's how he started. There are many other ways of explaining it, but you have these very good approximations. When you go with zeta of 5, the approximations are just not good enough to reduce the numbers to irrational. And a priori certainly made himself famous on this. And this is a lot, very simple. So, and then they have a beautiful conjecture which would solve this for any A of B, which is if you have a recurrent sequence like I wrote down before, that if you have UN plus 1 times A equals BUN plus EN, where this EN is between minus B and A. So if you have a recurrent sequence like this with fixed integers, relatively prime, and this is all integers, then their conjectures, this kind of thing forces UN, no matter what you choose the ENs, as long as they're integers, that always forces UN to be divisible by some prime infinitely often. So this would resolve the problem. But it's a very difficult thing to study a recurrence where you don't know what the EN is. So what really makes the problem really challenging here is exactly that feature. It's this unknown EN. And they've handled it in 2 cases. So I repeat, I hope I stated the theorem. Let me state it again. Theorem is so beautiful. This is the theorem that I have always, since I've seen it, found quite striking. The integer part, 3 halves. Let me just do this case, because 3 halves, that's already much longer and more complicated than 4 over 3. The combinatorics is more complicated. This is composite for infinitely many, that's the thing. The integer part of here is composite. For infinitely many. As far as I know, these 2 numbers are the only ones for which it's known. There may be some others that some people have adapted this proof further, but I couldn't find it on any reference on the Sarnak probabilistic. So today you can look at what came afterwards. In the old days you had to actually know something. Today you can just search these things, but I'm not so good at that. So that's a typical kind of theorem, meaning in this and in the previous paper and all my experiences with him and reading his book, which I'll talk about a bit later in the reminiscences, his love was to make his own original contribution, not to come with a big machine. One of the things that's very clear had a massive impact on him was the Erdős and Selberg proof, elementary proof of the prime number theorem must have been proved. It's 48, I assume he was a student at Princeton at the time, of MLRT. Because he wrote a lot about it afterwards, explaining how to use this elementary proof to prove all sorts of things. It's in his book, it's highlighted. He gets a story right, by the way. The Erdős contribution is correct. The Selberg, he keeps away from all this controversy that other people have fueled.
Wasn't he the first to generalize it?
He generalized it to number fields.
Progression.
And progressions, That's correct. To do the Dirichlet, right? I mean, so I think there he saw this technique and understood it. In this kind of problem, he invented the techniques. And the techniques are often completely elementary, but that's usually the hardest. Okay, so I have, I think, 15, 20 minutes in which I chose a topic for two reasons. One is the topic that I'll describe here. These are some brand new theorems that Bergen, Gumbert, and I are very happy to announce here on this occasion. I think Gumbert, whose voice disappeared and being punished for something, I don't know what, did talk on this once, but none of us have spoken about this before. And the problem I'll describe is exactly along this line. It's a more traditional problem, and it's about Markov numbers, about which, again, we know almost nothing, but hopefully when I finish, you'll see we know something. That's the visibility of Markov numbers. So let me spend 10 minutes reminding you what these are. They were invented by the mathematician Markov, whose name was spelled Markov at this point. When he changed fields from number theory to probability theory, Markov changed I don't know if he changed his spelling, but that's where the spelling of his name seems to change. Anyway, that's the original old papers. And he was very interested in the following Diophantine equation, which has the feature that the solutions are very sparse. It's got all the features I'm talking about and all the difficulties I'm talking about. And it's the following equation. It looks a bit strange, but it comes up all over the show. Okay, that's this equation. Now I'm going to look at this over many different fields. But my only interest in this world is the whole numbers. But to understand whole numbers, you have to understand everything else. Everything else, including finite fields, including complex numbers. As you'll see, they all are secretly there. But we'll be interested over the integers. In the meantime, let's just think of that as equation in F13 space. The Diophantine equation. If you homogenize this and make it rational, it becomes a boring equation, you read. So don't homogenize. It's interesting over the integers. This is where, and it's very much connected. Why was Markov interested in this? It's connected to the Lagrange spectrum, to the Diophantine approximation, to the best approximations of numbers by rational numbers. They're all encoded in these integer solutions. But I want to study, or people have wanted to study, this as a Diophantine equation. So the first thing you could ask is, well, what are the integer solutions? So firstly, there's a solution which has been set up to be there. 1, 1, 1. And if you'd make the dictionary of Markov between this and Diophantine approximation, this goes over to the golden ratio. That's not going to be of any relevance. So it's kind of the simplest of all numbers. And what Markov observes, so I'm interested in the solution and a Markov number, a Markov triple, and the Markov, so the solutions, the Markov triples that I'm interested in are solutions in integers and positive integers, strictly positive. Now there's a solution 0, 0, 0, which you can always remove. And you could have plus or minuses, but if you switch them, you have to switch them with a sign, so you can always arrange them all to be positive. So if you understand this, you understand all the solutions, positive ones, and these are called Markov triples. Now, this is one solution, and what Markov observes is that there's a simple Galois theoretic, I don't know exactly how you would say it, but if you fix x1 and x2 and you look at this as an equation in x3, it's a quadratic equation in x3. It's got one integer solution, so if I start with a solution, I've got x3, it's an integer. But there's another solution, because it's a quadratic equation, and that other guy also has to be an integer, if it's an integer, if the coefficients are integers. So there's a map from the solutions to the solutions, which gives rise to an affine polynomial map of A3, which is an involution, but we'll be composing these things. So let me write down this map immediately. Let's get it right. So I said if I fix x1 and x2, then if I take x1, x2, x3, this is the formula for the other root. So x1, x2, 3x1, x2 minus x3. It's not linear. This equation is not a quadratic equation. If you started with a quadratic equation, these roots would be linear. But because this has got a cubic on this side, this makes this a strange equation over the integers. It's not homogeneous. This move here, I'll call it R3, is clearly a polynomial map of affine 3 space into itself. Its square, if you check, just takes me back to the first root. So its square is 1. So it's invertible. So that in one dimension, there aren't very many interesting polynomials maps, unless you're linear with coefficient 1. You can't invert a polynomial map in one variable. But in two variables, you can have nonlinear maps like this, which are invertible. They square to 1. They're genuinely nonlinear maps. This is not so interesting by itself, but if I put in R1 and R2 similarly, I get a group generated by these 3 automorphisms of A3, and I'll call gamma the group generated by this. This is Markov's group of polynomial. Once I start composing these, the degrees of these polynomials are going to grow very large. You're not composing linear maps which stay linear. That's easy stuff. So there's polynomial automorphisms of affine 3 space, and it preserves integers. I start with an integer. This clearly preserves integers. The product and sum of integers. So this preserves integers, and I can look at the orbit of 1 under gamma. So this is an orbit. So if I take gamma applied to 1, 1, 1, I will get solutions to Markov's equation because I satisfy this is the equation. That won't change. And Markov's theorem is this is all the solutions. So if I apply, by the way, this is a Z2 free product. Z2 is an abstract group. Free product Z2. The only relations are that the square is 1. So it's a very big group. And
So you mean the group generated by those 3 in the group of polynomial?
Yes. And I take gamma applied to this, and this is all of them. So there's only one orbit. And this is proved, like in the old-fashioned days, by descent. What you do is you take any solution, and you show one of these moves makes the biggest coordinate smaller. And then after a finite number of moves, you'll end up with 1, 1, 1. You've got nowhere to go. So there's only one orbit, and it's a nonlinear action. And Markov is very happy. Now understands how to make all these solutions. That doesn't tell you what the solutions are. And if you iterate nonlinear maps, you have a lot of trouble to understand what you're doing. But it's I'm not iterating one map. I'm iterating the big non-commutative group. Okay. So Markov's numbers, which are intimately connected to this. So let me remind you what a Markov number is, because I want to get back to Harold Shapiro. So a Markov number, M, Markov number, is simply the coordinate of one of these, counted with multiplicity 1. You hit it more than once. Just a coordinate of a Markov triple. Any coordinate of a Markov triple with multiplicity 1. Now the number is any coordinate of a Markov. So you can work out what these numbers are. The first few. This group quickly goes moving out into infinity. The first few Markov numbers are this. 1, 2, 5, 13, 29, 34, 89, 169, 194, and so on.
So you're saying any coordinate?
Any coordinate counted with multiplicity 1. So actually there's a problem here that has beaten everybody. The guy who wrote the main paper on Markov numbers besides Markov is Frobenius. And he apparently, but it's not clear that it's in the paper, but Castles who writes about this, says that he asked this. And if you order the Markov numbers according to size, with the biggest one, the conjecture is then you only get each one once. That's called the uniqueness conjecture in Markov triples. And that's one of the big unsolved problems that you will see, just like with Riemann and all these other problems, people are solving all the time. Anytime anybody reads it, they find a mistake. So this has not survived any But there have been many claims to solve that. That's a difficult problem. I have nothing to say about it. But if you, but let's assume it, just to explain something, yeah? Suppose I look at these numbers and I look how many numbers there are up to t. How many Markov numbers there are up to t? So this is a lovely theorem of Zodiac. There are many ways to prove it today using Teichmuller dynamics, using other techniques. It's connected with Markov equations connected with the moduli space of the once-punctured torus, something Magnus understood very well, by the way, and many other people. So I don't know why I should never erase the key equation. X1 squared plus x2 squared plus x3 squared. x3 x1 x3. The number of m in m such that m is less than or equal to t is about log t squared. This is the theorem of Zodiac. In his youth, from his youth, C positive, he gives an exact infinite series for C. It's quite complicated. Log t squared. So this is a very Lacandry sequence. It's a little fatter than 2 to the n plus 5, which would only have a logarithm number of numbers up to t. And that gives us a little bit of hope that maybe we can say something more trivial about this. So the question is, are there infinitely many primes here? Well, I'd love to answer that question. We can't even do that with n squared plus 1. This is a very Lacandry sequence. But we don't know what's happening modulo p here. And if I could look modulo 5, as you'll see in a second, and answer at least that there are infinitely many composites, but I'm much more ambitious. Okay, so when you see an equation like this, you can ask what happens if I reduce mod p. This is a Diophantine equation. Reduction mod p is not funny like it was with integer part. This is a completely natural, standard, central problem. What is the reduction of that mod p? Okay, I want to try and answer that. And for that, there's some obvious combinatorics that's going on here. And that's got to do with the following. That let's look at the solution. So if I let xp star, this just means remove 0, be the solutions of the Markov equation of star mod p. See, if I want to do a servo-any Diophantine analysis, I must know what's happening with p. I want to ask, and that's what the strong approximation in the title is. What happens when you reduce Markov numbers mod p? All right, so let xp star be the solutions of this mod p. Well, clearly I'm going to land up. I started with integer. I'll have something which is not 0 mod p. That's these guys. And R1, R2, R3, these three affine morphisms, polynomial maps, which work on anything, they also work mod p. And so I can make a graph. So we'll call this the Markov graph. Which has got coordinates x, whose vertices are x star p, the solutions mod p. And I join any x here to R1x, R2x, and R3x. So each x, I make a Markov move, and it joins me to 3 guys. I get a 3 regular graph. I'll call that the Markov graph. The reduction mod p, so Markov showed that that was this descent argument. 1, 1, 1 gave all the integer solutions. So if I take the point 1, 1, 1 in this graph, these moves will move me somewhere, and that'll be exactly who I get mod p. But nobody said this graph's connected. So I'm very interested in the component of 1, 1, 1 in this graph. Since I have no idea what's going on, wouldn't it be nice if it's connected? Okay, so this graph, nobody said it's connected, but that's the big conjecture. Alex Gumber checked this already 10 years ago. When we started this, we developed with Bergan a theory called the affine linear sieve. Precisely, we were trying to sieve on Markov triples, and we hit so many problems because it's not linear, because these morphisms are not linear, that I suggested, and these guys listened, let's be honest, let's just make the affine maps be linear first. And let's try to develop a theory there where you have morphisms of affine space which are linear, they have a finite number of moves, and try to understand the reduction mod p and do a Brun sieve. That's a big theory today. It's complete. We started off in SL2, covered with gain. Health got many very important contributions. The final thing in complete generality has a whole list of contributors, including Green, Cal, Rouillard, P-Bird, Sabo, Vaju, Salehi. It's a big industry. It's a complete theory. We can do the affine surf if the moves are linear affine maps. But it was always the nonlinear that we were after, and everything there is infinitely harder, and things are much sparser. In the other case, the number of numbers up to t so is a power of t, not log. So this has got all the difficulties in it. And so the basic question is strong approximation. Is strong approximation true? I.e., is X star P connected? That's equivalent for all P. So I'm going to tell you what we know in a second, and that will allow us to start doing a survey and answer many questions. So we do know a lot about this now. Alex checked this many years ago. As I said, 10 years ago, he took these Markov graphs, and they're up to 500. Everything was connected, so we assumed they were even what we call today expanders. They have a spectral gap for their connectedness, which is very important in the affine linear circle. So it seems that what we want to be true is highly true. But that's the nature of the beast. The minute something is random, everything is true, but it's very hard to prove. This is much more random. These moves are much more random. Anyway, so is it connected? And we, of course, believe it was connected. However, if you sit on something for long enough, somebody else will make the conjecture. So this actually has appeared in print since, and I want to give them credit because they came up with this conjecture certainly without knowing anything we were doing. The color. And this is in connection with group theory. Nielsen moves a la Magnus on the character variety of the once punctured torus, and they come up exactly with the conjecture of which a special case is this strong approximation. And Wonderley. I gave a lecture recently, a public lecture in Oklahoma, and this guy's from there, but he'd already retired and went to Florida suddenly. But he's got a great conjecture. It contains the statement. So the big conjecture is strong approximation true? Are these graphs connected? If you reduce Markov numbers mod P, do you get everybody that you're allowed to get? Okay, that's the big conjecture. Is strong approximation true? And the conjecture is yes, it should be true. They don't prove anything. They just run a numerical experiment. I'll get back to the Markov numbers. So here's what we can prove, and the techniques are the main thing I want to emphasize is techniques go beyond the Riemann hypothesis. If anything you want to remember, that's what's most important here. The Riemann hypothesis ain't good enough in the function field, in the finite field case. And I'll explain a little bit of that. So here's theorem 1. So all this is joined with again. And then I'll state what we can say about compositeness, which is exactly the kind of Shapiro question. Again, Gambit. Myself, I should have said there is one theorem. So basically nothing is known about Markov numbers. I'll get to that. One theorem of Zanier and Kovaya, which is quite striking. But otherwise, as far as I can see, nobody's ever proved anything about Markov numbers. So this is the theorem 1. Okay, the theorem 1 is about all primes. The theorem 1 should read, it's true. Unfortunately, we can only prove that there's a massive component for all primes. This theorem 2 will say that this theorem, so just to give you, the theorem is true. The exceptional primes, the set of primes for which it's not true, is tiny. So that's already good enough to say. So theorem 1, there is a component, a giant component, we call it, C of P of X star P, this Markov graph. Now remember, 1, 1, 1, I don't know if it's in the giant component. So it's hard to use just directly like this for purpose here. Anyway, there's a giant component. That is to say that X star P, so that's a connected component of the graph. X star P remove C of P is less than, we're only interested when P is large. The end game, once we finished everything up, will involve computation. If we were to finish everything up, then we'd have to get constants. Right now, for any epsilon positive, this exception, the guys that aren't in the giant component is at most P to the epsilon, and the cardinality of X star P is very easy to compute. It's just the number of solutions over the finite field is P squared. So this is saying that the exception, the giant component is giant. It's a giant component, and it's very important to us because the whole philosophy of this proof is to try and make Markov moves to get into the giant component, connect yourself up to the big guys. The big guy. All right, so that's theorem one. That's true for all large primes. And theorem two, which uses quite a bit more, including some GM-Lang conjectures and things like this, theorem two, is that the conjecture is true for most primes, but in a very strong sense. Let E be the set of primes, prime numbers, primes P, for which a strong approximation fails. Then E intersect the interval 0t, so the number of primes in this set in the interval 0t is at most t to the epsilon, or any positive epsilon. So it's much more than most primes, it's true. It's the exception, and we can improve that. We haven't improved that to the set is finite, which is the main goal, of course. But that's already extremely powerful. This is saying that the strong approximation is true for, and the enemies are primes for which p minus 1 is very, very smooth, meaning p minus 1 has many, many, very small prime factors.
Like in cryptography.
It's exactly like in cryptography. It's all about orders of elements. Exactly. So that's that. And now let me apply it before I say one or two words about the techniques, which I obviously don't have time. I just want to apply it to the Markov numbers, because that's the Shapiro question and the one we were after. So I'll put theorem in a little t. Apparently Mumford said if you, that doesn't mean we haven't got a proof, we haven't written it up completely. So that's what theorem with T means. Almost all. So we have to generalize this to composite Qs, which are products of these primes. It gets much, much more complicated. Enough to make this argument true. So almost all Markov numbers. So remember, in this case of Markov numbers, it's very easy to produce infinitely many guys which are composite. But the problem that you want to show is that the set of the guys which are composite are most of them, almost all of them, meaning the number up to x is asymptotic to the number that you have. Or the number up to x which are prime is little o of the total number. So that's what almost all means. Almost all Markov numbers are composite. Very sparse sequencing, and that, of course, applied. We do some sifting theory, very elementary, not a Bruns or anything that fancy. But the most important input is to understand what's happening modulo many primes and products of many primes. All right, let me just say a word about the strategy, because this has a feature which is actually similar to the kind of thing. This doesn't fit into any standard mathematics, and that means, in my world now, combinatorics is going to say this. Combinatorics, which is certainly what Shapiro loved about. You know, that you can't use algebraic geometry. The pigeonhole principle is your main thing. So where's that coming from? What's that going to do with this? So what you do here is you start off with X. So let me tell you the basic strategy, and then two approaches to it. One which is really combinatorial, and one which is an algebro-geometric attack, which works, but is based on something which is better than Bayes' proof of the Riemann hypothesis. Better. So we're starting with something like this: x1 squared plus x2 squared plus x3 squared. Not something like this. You work on this long enough, you write the equation no matter where you walk. This is the equation, and you have these moves R1, R2, R3. Now, if I fix x1 and I apply R2 that just fixed x2 and it did an involution. Suppose I do R2 times R3. This now fixes x1 and it's moving x2 and x3. So if I fix x1, it's going to clearly take the conic. If x1 is fixed, this is a conic section. And whatever this thing's doing, it's taking this conic section back to itself. And a conic section like that is a hyperbola or parabola over the finite field. I'm working over FP. So the question is, clearly this is going to be a rotation, and it's going to have some order as a rotation. And everybody that I rotate, my guy that I start off with, to, will be connected. That's the definition of the graph. I'm trying to connect myself to everybody. First thing is I start off with some guy, and I want to just connect it to something bigger, some orbit. I want to just keep on connecting to orbits which are bigger and bigger and bigger until I run out of space, and I connect myself to the giant component. So I want to make sure, so I have to compute the order of this rotation, which, that's the beauty of just this guy. The first guy was an involution. This guy is still a linear map. It's a rotation. If I apply this composed with something else, then the degree will grow. But this guy, I can rotate because it's fixed x1 and it's moving this conic section by rotation. So this guy's got some order. And that's where p minus 1 is going to come up. What are the orders of the elements of rotations in SL2FP? Well, the order of the group SL2FP we all know. The orders can be p, which is very friendly. P minus 1, that would be some root of unity in FP. And p plus 1 would be a root of unity in FP squared. That's where the eigenvalues of this rotation can lie. And our enemy is that this order is very small. If the order is big, I'll have a big orbit, and then I can go look there to find from that orbit friends of it that are connected to even bigger orbits. And just keep on making, so as long as I can find a guy I'm connected to whose order of its associated rotation for one of its coordinates is bigger than when I started off with, I'm going to make progress and connect myself to the cage. And that's the whole attack. And the question of doing that boils down to some algebraic geometry, because you'll quickly land up to an equation like this. I'm going to say key equation and say words about it and stuff. So the key equation, it'll be over Fp, is 1 over Fp squared, I'll ignore it. Y plus sigma over y equals x plus 1 over x. And y here is in this group generated, so y is in H1, and x is in H2, where H1 and H2 I'll for simplicity assume that H1 and H2 are subgroups. This is where the eigenvalues lie.
Did you want y and h1?
Y is in H1. Thank you. X is in H2. These are subgroups of Fp star, and order is p minus 1. So p minus 1 has very small prime factors. This is my enemy. I might start off with some guy which has got small order. Anyway, I want to make sure I'm connected to a guy who's got a bigger order. So the sigma is not 1. Otherwise, so this is a non-trivial curve in the plane, in Fp star. And the important thing is that the guys I'm looking at are lying in subgroups whose size I have no control over. But I can assume that, say, H1 is bigger than H2. And what I want to show is that the set of solutions to this, so the trivial upper bound for the number of solutions here is clearly the cardinality of H1, because once I have Y, this guy's only got 2 choices. So basically, twice H1 is a trivial upper bound. So the theorem we prove, no matter how small H1 is, that the number of solutions to this equation, no matter how small H1 is H1 to a power 1 minus tau with some universal positive number tau. So this is the key theorem, and it can be proved in 2 ways. This is the key equation, and the key theorem is that the number of solutions here, which is trivially at most H1, P is going to be large, is at most H1 to the 1 minus tau, and tau is a fixed positive number that we haven't computed, though in one of the proofs the number was like 1/5. I'll say just a couple of words like that. So, now, let me explain what this got to do with the Riemann hypothesis for curves. If you look for solutions to points for curves of a finite field, and you rewrite this in terms of characters, or if you rewrite this in terms of the fact that the orders are small, it's very easy to see that if the cardinality of H1, if what you started off with is bigger than square root of P. So there's something about the Riemann hypothesis which says you can never go beyond square root cancellation, because that's where the zeros of the Z function are. So you can only count things up to leading order and square root. So as long as things are bigger than square root, you have every right to expect it will tell you what's going on. So as long as the cardinality of H1 is bigger than p to the half plus delta, this lemma can be proved using Bayes' Riemann hypothesis for curves over finite fields, and we're done. So once we start connecting and connecting, once I get beyond p to the half plus delta, I can stop all the steroids and just use Bayes. But when I start out, h is extremely small. And what happens is Weil is completely useless. What Weil will tell you is the number of points on a curve of genus G over the finite field P, Fp, the number of points is P plus 1 plus a remainder, which is at most square root P. Those are the eigenvalues of Frobenius, so that's fantastic. But then there's also the genus. And if the genus is bigger than root P, this kind of statement is absolutely useless. And that's exactly what happens when H1 gets less than root P. All of a sudden, the genus of the curve that's trying to control these roots of unity has gone bigger than root P. And algebraic geometry is all over. Combinatorics to the sieves. There is a proof of the Riemann hypothesis by Stefan. It's there, not the real Riemann hypothesis. For the phase theorem about curves over finite field. And it's based on constructing polynomials which vanish to high order to give an upper bound for the number of solutions. And it's a completely elementary proof in this case of curves. It's never been generalized to higher dimensions. It's based on what combinatorists today call the polynomial method, which is the way you give upper bounds for counting configurations by making polynomials vanish at the set of points and then showing it's not zero and then just using simple algebraic geometry about the number of zeros. This is a standard method in transcendence, and you have to construct these polynomials. And that proof, sometimes when the genus is large, will give you information which is useful. And this is a case where you can take Stepanov's proof, adapt it by very elaborate construction of polynomials that we struggled with. And we haven't got completed the most general case even, but it works in this kind of setting. And you get this fact here, no matter how small h is. So you can start with h small. Remember, your aim is you want to connect yourself up to the cage. And you've got guys with a small order, and then you're saying, all right, I'm going to be connected to somewhat bigger order. I intersect that, well, that's smaller, so I'm going to at least by pigeonhole have one guy with bigger order. So this will work handsomely, but only because Stepanov saves you, because it gives much better bounds. In very special cases, it gives the full Riemann hypothesis. In general, he gave a proof. But if your curves are got specific equations and you can actually construct these polynomials, which we do, then you will do better. That's one proof. Comes Bergen, he finds another proof. He's found a purely combinatorial proof using aversion, so I'm running out of time. I was going to write it down. And I thought that Gumbert would explain it before, but pre-talk. So he's got there's a theorem called Semeretti-Crotta theorem, which is about incidences of planes and lines. And it gives an upper bound just in Z2 or in R2. This is a real theorem about the upper bound for the number of incidents between planes and lines. You can imagine that this has got upper bounds, is connected with upper bounds between hyperbolas, because we're acting with these linear fractional transformations secretly. So you want this Semeretti-Crotta theorem over a finite field, which is of a very strong type. And Bergen proved this a couple of years ago, using a technique of flattening, which he and Gumbert invented to prove a spectral gap in the linear surf. So it's kind of a beautiful story that that aspect has come, and it's not immediately apparent what it has to do with this equation. You square this, and then you change variables, and you land up with a situation where you can use Bergen's rather remarkable Semeretti-Crotta theorem, which is a very short note in Contrandu of a year ago. And that's a very robust method, and in fact, it's a method we're using to handle Q as well. So the kind of beef of this whole thing is beating Riemann here on small sets. And harmonic analysis and Riemann can only deal with sets which are square root or bigger. Combinatorics can apparently do with small sets, and that's without that you'd be sitting in a small component and never know you had it. Thank you. So I hope Harold would like it.
I'm sure Harold would have loved it. Do you have time for a couple of brief questions?
We will be posting this paper next week.
And those of you who signed, there's a sheet which should be returned to me to get video of this, which will be made available by the Shapiro family member. Any questions? Okay, I guess everybody wants food. So we're adjourning now to meet again over on the 13th floor lounge in Courant, where there'll be a reception, food, drinks, and some reminiscences. Thank you very much. Let's like the speakers.